What's up, ladies and gentlemen? In this lesson, we are going to cover simplifying identities. This is a complete lesson on me teaching the simplifying identities. We're going to have notes as well as multiple examples. So if you want access down to these notes or this document, so therefore you can work through it on your own as we're going through this video, then the links will be provided for you down below. Also, if you'd like access to my Precalculus Simplified course, which goes through this content as well as many more, and also a condensed version, then you can go and check that out. The links will be down below. So this is just like I would teach inside of the classroom. So just like with any lesson, we want to start with a warm-up, something to get our brain kind of thinking of what exactly we're going to be teaching in this lesson, drawing from the stuff that we already know. So the first one is write an expression of tangent in as many different forms that you can come up with. So a lot of times students will, obviously they think of the obvious, that they remember that, well, I remember the tangent of theta, going back from our geometry days, that is going to be the opposite over the hypotenuse. And then students were like, oh yeah, but I remember also in trig that in the last lesson, we also dealt with when we have a coordinate point on the unit circle, that we can represent tangent of theta as y over x, right? And that is good. So the thing about identities is an identity is basically just going to be an equation where we're going to have the left side is equal to the right side. Now, the thing is, the identities, they don't have to look exactly the same, right? They're just the values have to be equal or true. So like the left side, you could have 10 minus 5, and on the right-hand side, you could have 5, right? The left and the right, they don't look the same, but they are an identity because the left side is equal to the right side. So that's basically what we are going to start with, is some basic trigonometric identities, and then we're going to use that to simplify trigonometric expressions. So the first identities we're going to look into is the quotient identity. So the tangent of x is sine of x over cosine of x, and cotangent of x is cosine over sine. So let's just do a quick review of like where these come from, like why we have these, because it actually come from stuff that we can basically reason with and understand rather easily. So if we think about the first quadrant on the unit circle, and we say, all right, well, if I have a point, right, x comma y, we know that the distance from the origin to that point is going to be 1, right? Because the radius circle has, the unit circle has a radius of 1. And we'd say, all right, well, this is going to be our theta. And we know that we could also create a right triangle from this, right? That's how we created the unit circle. So this would be represented as x, and this would be represented as y. Now, the important thing that we can look at with this is we know that if I was going to look at this triangle, and I go back to my original definition here, tangent of theta is opposite over hypotenuse, or also we could say tangent of theta is y over x. So if I say, all right, tangent of theta equals y over x. Now, how are we going to get to the sine of x and cosine of x? And that's where it comes into like, oh yeah, I remember when we were evaluating, right, on the unit circle, remember the sine of theta was equal to y, the cosine of theta was equal to x. So now I can just use some substitution here, and I can say, well, if tangent of theta is y over x, I can also rewrite that as y as the sine of theta, and x as the cosine of theta. And therefore, you can see how that identity makes sense. And then you can see cotangent, that's just going to be the reciprocal of that cotangent identity. Now let's get into the reciprocal identities. Now, the reciprocal identities, again, is very similar with our understanding of special right or just right triangles. So if you think about the sine of theta, right? If you remember that, that was opposite over the hypotenuse. Now, again, if you kind of think about going on the unit circle, we could rewrite that as the sine of theta, the opposite side, right? That was going to be y, and the hypotenuse is 1. And then the sine of theta was just represented as y. Now, similar, if we think about the cosecant, and the cosecant of theta, then it was going to be the hypotenuse over opposite, right? Those are reciprocals of each other. And so therefore, when you think about this in terms of y, then this is going to be a 1 over a y. And then if you want to look at how cosecant then is going to relate with sine, we can just rewrite a cosecant of theta, a y as a sine of theta. So you can see the cosecant of theta is simply just going to be a 1 over a sine of theta. And you can see that's how that one goes and works out. And then over here, you can see how they just go back. So if I have the cosecant of theta is equal to a 1 over sine, like how am I going to get back to sine of theta? Right? How can I get this now relationship to now solve for sine? Well, if I wanted to solve for sine, I would have to get it off the denominator. So you multiply sine of theta on both sides. And then what you would have here is going to be a sine of theta times a cosecant of theta is equal to 1. And again, if we wanted to solve for our sine of theta, we divide by cosecant of theta, divide by cosecant of theta. And now what you can see is we'd have a sine of theta is equal to a 1 over a cosecant of theta. So I worked with this for sine, but ladies and gentlemen, you can do this for the cosine as well as do this for the tangent. So you can see how these reciprocal identities are going to work and that they are true. Now, the next one is going to be even odd identities. Now, a lot of times students kind of get these even odd identities like messed up. They kind of forget, like they don't understand how they can work. So I'm not going to go through all of them, but what I want to do is just kind of show you looking at the graphs. And if you can understand, if you can remember what the graphs are going to look like, in my opinion, it's a lot easier to remember these identities. So let's go and first look at the sine function. If you're going to look at the sine function, and let's see, we have initial period, looks something like this, and then go over like that. Okay. Now you got to remember what happens when we take the reflection. Actually, well, let's just look at this point. Well, let's look at this point right here. So that point, look at it right there. All right, that point is going to be at a pi halves, if you remember from the unit circle, and graphing. So this coordinate point is at pi halves, and remember the y-coordinate is going to be at 1. So what they're saying is, well, what about at negative pi halves? So if you look at negative pi halves, so this would be at negative pi halves, what is our value? Our value is going to be at negative 1. Right? So you can see when I take the sine of a negative angle, so instead of sine of pi, we know is at 1. Sine of negative pi, you can see, is also going to be at negative 1. Now, again, that's going to be true for the exact same thing, even if I was to look at the cosecant graph. If we were going to draw this exact same graph, and we were going to do the cosecant function, remember the cosecant function is just going to be these reciprocals of these graphs, right? And we have some asymptotes right here. And then you'd have that point right there, and it's going down. So again, what I want you to see is, let me actually just write this out. If I have the sine of pi halves, that's equal to 1. The sine of negative pi halves is equal to a negative 1. And ladies and gentlemen, this is true, the exact same thing over here. If I say the cosecant of pi halves, that's going to equal to a 1, right? You can see that value is right there. And the cosecant of a negative pi halves is going to be equal to a negative 1. So we're dealing with the sine, the cosecant. Whenever we're taking the negative of that angle, the value is going to be the exact same. It's just going to be the negative version of that. Now, we can also look at this in terms of like the cosine graph. Because hopefully you remember like the cosine graph, well, yeah, that looks very, very similar to the sine graph, right? So now in this one, it has a vertex over here, and it's going to go up and down in this case. And then over here, we can go down. All right. Now in this case, rather than looking at pi halves, let's go and take a look at pi. So pi would be roughly in this one. So that's pi halves. There would be pi, and then pi halves would be over here. What I want you to see is when I say, what is the cosine of pi? That's equal to a negative 1, right? Cosine of pi, that's equal to a negative 1. Well, what about the cosine of negative pi? You can see, ladies and gentlemen, they have the exact same y value. These are symmetrical about the y-axis. So the cosine of, sorry, I should probably use parentheses there. Cosine of negative pi is also going to equal to a negative 1. And ladies and gentlemen, we can again do the exact same thing here with the secant graph. All right, because again, remember the secant graph is just going to be the reciprocal of that. So it's going to look something like this. So you're going to have here, And then you're going to have these points here, and you're going to have some asymptotes. Asymptote looking right there, and an asymptote looking right there. But again, the exact same thing that I want you to see. If I take the secant of pi, that is simply just going to equal to a -1. And the secant of negative pi is also going to equal to -1. So the important thing when looking at this, when you're looking at the cosine and secant, so cosine and secant are the only time when you take the negative angle, you're just going to get that exact same, you're going to get the exact same as the original. So if it's a cosine of -x, it's the exact same as a cosine of x. All right. But however, sine, cosecant, tangent, and cotangent, which I don't have enough room to show you graphically, but hopefully you can see they're exact same thing. Now, the next one is, again, something I think we can easily kind of remember, but sometimes, a lot of times students get tricky because it looks confusing, right? You look at this and you're like, what the heck is going on? Sine of pi halves minus x is equal to cosine. So again, what I like to describe this to my students is to remember, ladies and gentlemen, these are transformations on a graph, right? If you're going to take a look at this pi halves minus x, right? What exactly transformations are going on? Well, what we could do is we could rewrite this as a -x plus a pi halves, and then we could factor out that negative. So therefore, that's a x minus a pi halves. So what's actually happening to the graphs? What we're doing is we're reflecting it about the y-axis, and then we're shifting it pi halves to the right. So again, let's go and take a look at the sine graph and kind of see, well, how does this then work? How can we see that the sine of pi halves minus x is going to equal to cosine? So again, let's just draw a quick little sketch of this sine graph. And when you do that, let's see, you got this. We're not going to be perfect. That's not the sine graph. So we're not even going to be worse than perfect. We're going to be wrong. We don't want to do that. All right, let's just take the initial period, okay? So if I take this initial period and I reflect this graph about the y-axis, right? Basically what you can do is you can think about this graph is now going to look like this, okay? And then if you shift it pi halves over to the right, look what's going to happen. Now this graph looks like it's going to be the tangent graph. And what I want you to see is, yeah, that's exactly right. What's happening now is when you reflect it and then shift it pi halves to the right, you now have the exact same graph as the cotangent graph. So let's go and take a look at, if you can see that, that's exactly what's going on there. So let me actually just rewrite this. So I'll have, so if this was going to be this would be y equals a sine of x. And then if we're going to apply those transformations, then you can see that this graph is now going to look like the cosine graph. So y equals a sine of pi halves minus x. Okay, and that actually is the exact same thing as y equals a cosine of x. So the way that I like to remember these is I like to remember them by their groupings. If the graphs look the same, then what we call these coffunctions are going to be exact same. So we know sine and cosine, right, are very similar to each other. I can't go from sine to cosecant, right? Or I can't go from sine to like cosecant of this. So you can see like this has asymptotes, this does not, right? This is continuous, this is not. So I can't apply some transformations to go from a continuous function to a non-continuous function. So we know that the cosine and cosine are going to be grouped. In similar fashion, tangent and cotangent are going to be grouped. And that's why we have the cosecant and secant are going to be grouped. So we could apply these exact same transformations to the graph of cosecant and secant, and we'd get the exact same thing. Now, let's go and take a look at least the tangent graph, just to kind of see again, like make sure, like, all right, I think I believe you, Mr. McLogan, but let's just take a look one more time on this cotangent graph. So if I had, let's see, y equals tangent of x, I know the initial period of that graph is going to look something like this. So we know it kind of looks like that cubic function, right? We're going to have a asymptote here, and the asymptote, remember, is at pi halves. And then we're going to have another asymptote over here, and that's at negative pi halves. Okay, so let's go and see what the graph of y equals a tangent of pi halves minus x, or if we just like apply those transformations, add shifting it to the right and reflection. So if we looked at this, let's see, pi halves minus x. Okay, so again, take this graph, right? If we reflect it about the y-axis, it's going to look like this. Now let's shift it pi halves to the right. So I'll take this little thing here. I'm going to take this. If I move this pi halves to the right, then wow, that looks very, very similar to what the tangent graph would look like, right? Because the tangent graph, if you recall, or I'm sorry, cotangent graph, the cotangent graph has a y-intercept at pi halves. It has an asymptote at pi. And yes, ladies and gentlemen, that graph, it's not perfect that I have here going on, but that, boom, is exactly what we're looking at for the cotangent graph. So you can see how they relate. You just got to think about these as the transformations. That's the important thing that I want you to remember for those. And if you can just remember what the graphs, which graphs are similar to each other, it's really easy to remember these cofunction identities. All right, last but not least is going to be the Pythagorean, and then we're going to get into some examples. Now, to remember the Pythagorean, there's a couple things. I remember when I was in school, and I was taking precalculus, the one thing my teacher was like, you got to know this identity. You got to remember it. And I remember when I first started teaching precalculus, I was like, man, I forgot so many things on precalculus. But the one thing I didn't forget was sine squared plus cosine squared of x, of cotangent of x is going to be equal to 1. All right. So again, let's go and take a look at what that is. So we know this coordinate point, this is going to be a xy, and we know that the radius or the distance from there is going to be 1. We could say this is going to be our theta, and we know we can create a right triangle because that's how we created the unit circle. And we could say, all right, that is going to be your x, that is going to be your y. Now, a couple things we need to remember. If we were going to use the Pythagorean identities, we could say we could create a Pythagorean relationship here, right? We could say that the x squared plus y squared is equal to 1. Whenever we have a right triangle, we know we can use the Pythagorean identity. So the important thing, though, to remember is going back to our understanding of x and y with cosine and sine. Remember that the x is the same thing as the cosine of theta, right? We already made that substitution. And y is the same thing as the sine of theta. So by using our understanding of coordinate points on the unit circle, x, y, as cosine of theta, sine of theta, if we just now replace this x with the cosine of theta and this y with the sine of theta, ladies and gentlemen, we now have the Pythagorean identity. So this is going to be the cosine of theta. What am I writing? Tablet's being a little iffy. So we have the cosine squared of theta, which is how we write it. We don't write it as cosine theta squared because then that kind of treats it as like the theta is squared. So you can use parentheses and say cosine of theta quantity squared, or you can just write the squared right after the cosine. And then plus here we'd have a sine squared of theta is equal to 1. Now, the definitions that I used here was x, so x is representing the angle in these definitions, whereas here on my diagram, theta represents the angle. So that's the difference. All right, now you might be thinking, well, cosine of theta plus sine squared of theta is equal to 1. I got that. How are you getting these? Well, again, just like we did some algebraic manipulation in the reciprocal identities, we can do that over here too. So if I have the cosine squared of theta plus the sine squared of theta, and we know that's equal to 1, right? Now, if I want to be able to, let's say, divide everything, as long as I'm doing everything on the same side, and then I'm just creating an equivalent equation. So if I go ahead and divide everything by, let's just rewrite it like this. If I divide every term, both sides, by cosine squared of theta, let's see what's going to happen here. So that's a squared. And then if I divide this by a cosine squared of theta, and then this by cosine squared of theta, I would now get a 1, right? Cosine squared of theta plus divided by cosine squared of theta. It's the same thing divided by itself. It's going to equal 1. Over here, we know that's the quotient identity. Sine squared of theta over cosine squared of theta is now going to be a tangent squared of theta. So that's a tangent squared of theta. And then via the reciprocal identities, 1 over cosine squared of theta is now equal to a secant squared of theta. And you can see that is that one right there. So again, hopefully you recognize, well, Mr. McLogan, can we do the same thing with sine? Of course we can. So why don't we just go ahead and do that? So again, we take our original Pythagorean identity, which hopefully you are not going to forget, and then we just do the same thing. Instead of dividing everything by cosine, now let's just go and divide everything by sine, or sine squared of theta. So I take the sine squared of theta, divide this one by sine squared of theta, and take this one and divide it by a sine squared of theta. Now over here, again, using our quotient identities, cosine squared over sine squared of theta is going to be a cotangent squared of theta. Same thing divided by itself, we know it's going to equal to 1. And again, the reciprocal identity tells us this is equal to a cosecant squared of theta. Now, ladies and gentlemen, be a little careful, or just recognize here, this is as 1 plus cotangent squared of theta. This is going to be cotangent of theta plus 1. It's the exact same thing, right? 2 plus 3 is the same as 3 plus 2. And the thing about identities, which I mentioned at the beginning, things don't always have to look exactly the same, right? And that's really, really important. And sometimes it's a mental shift for students to have to be able to take once we start getting into examples, is this understanding of things can still be exactly the same value, but they don't have to look the same. Now, obviously, you could just go ahead and rearrange that on the cumulative property, but it's important to see we're going to be doing some manipulations so that we can simplify these trigonometric expressions. So let's get into these examples and get some practice, right? Some just basic ones to kind of see like, well, how do we simplify? So simplify the expression to one trigonometric expression or number using these identities. Now in this one, I say the reciprocal and quotient identities. And just remember, our idea to simplify things, right? We don't leave 8 divided by 4. We divide it through, right? 8 divided by 4 can be simplified to 2. We usually don't leave a fraction 3 over 6, where we simplify that to 1/2. So identities, if we can divide things from the top and the bottom, then we're going to want to do that, right? If I have a sine over a sine, we can simplify that to a 1. So one of the key tips that we want to think about is using that division property, trying to get the same expression in the numerator as well as in the denominator, because they're going to divide out. So just like we did with 8 over 4 and 3 over 6. So a lot of times one of the key tips is to rewrite things in terms of sines and cosines. And you can do that by using the reciprocal or the quotient identities. So in this case, I have my sine of x, that's written in sine, but cosecant of x, I can rewrite as a 1 over sine. So if I look at this, I have a sine of x times a 1 over a sine of x. Well, obviously, ladies and gentlemen, sine of x is simply just over 1, right? You can always write something over 1. And so if we were to multiply these across, you'd have sine of x over a sine of x. So we don't think about they cancel each other out, but no, they divide to equal 1. Over here, I have cosine of x equals tangent of x. Now, here's a mistake that students will make. They'll say, well, I remember the reciprocal identity, cotangent or tangent can be rewritten as 1 over a cotangent of x. And that is actually true. And this is what kind of gets confusing about simplifying identities. You're right, tangent is 1 over cotangent of x. The problem is I can't simplify this, right? Cosine and cotangent do not divide out, right? They have to be the exact same expression. So what can we do? Well, let's look at a different identity. Rather than rewriting tangent of x as 1 over cotangent of x, what about if we wrote tangent of x as sine of x over a cosine of x? Now, as you think about multiplying these across, I'm going to use these little lines to divide them out. But again, they're not canceling out, right? They're simply just saying cosine over cosine, we know divides to 1. So now, those are now going to divide to 1. And you can see that my answer is just going to be a sine of x. Now, yeah, those are divided out. So now let's go and take a look at secant. Well, I know secant can be rewritten as a 1 over a cosine of x times a sine of x. And if you just multiply these straight across, again, you're going to get a sine of x over a cosine of x. So now we just need to remember, well, what was sine of x over cosine of x? Well, remember, that's a quotient identity that represents tangent of x. Cosine over sine, again, they don't divide out, but you can see that these are going to divide into not sine over cosine, but cosine over sine. Sine over cosine is tangent, so cosine over sine is going to be the reciprocal of that, which is cotangent of x. All right, now let's get into some fun ones. So a number, anything divided by its reciprocal. What would this look like? So I guess the best way to kind of think about this is, let's go ahead and rewrite this in terms of sines and cosines. So if I had sine of x over cosine of x, and then that's going to be all divided by a cosine of x all over a sine of x. Now, what do we do when we have a fraction divided by a fraction? Some people have some things to remember, like, was it like flip, negate, flip? I don't know. I hate all those things. The main idea, ladies and gentlemen, is you want to get rid of your denominator. To get rid of your denominator, you want to multiply by a value that's going to make it equal to 1. Because like 4 divided by 1 is just 4, right? We don't need the denominator anymore if the denominator is 1. So I got to think about what can I multiply cosine of x over sine of x to get 1. And hopefully you remember anything multiplied by its reciprocal is equal to 1, right? 1 over 3 times 3 over 1 is equal to 1. 2/3 times 3/2 is equal to 1. So if you want to look at this, what we need to do is just multiply by the reciprocal. Sine of x divided by the cosine of x. And then over here, do the exact same thing. Sine of x divided by the cosine of x. Now, when we go ahead and do this, these are going to, obviously you can see that the cosines are going to divide out. The sines are going to divide out. And then here we have sine of x times sine of x. Well, again, is just like, remember, you got to think about that. Sine of x times sine of x is going to be a sine squared of x, and cosine times cosine is going to be a cosine squared. So what we have is going to be a sine squared of x all over a cosine squared of x. Now, you might see that simplified there, but remember, if sine over cosine is tangent, then sine squared over cosine squared is going to be a tangent squared. So that will be a tangent squared of x. Now let's go and take a look again at this one. Same kind of idea, right? Your same thinking here is I can rewrite tangent as a sine over cosine. So let's go ahead and do that. So I'll have a sine of x, or sine of x divided by a sine of x over a cosine of x. And again, I'm just going to multiply by the reciprocal. So when I multiply by the cosine of x over a sine of x, here it's really important to remember that the sine of x on my fraction in red is in the denominator. But my sine of x over here is typically in the numerator, right? We can rewrite that as over 1. So now, as I multiply these, I'm just going to be left with a cosine of x. Because again, think about this. You can always rewrite the sine of x over 1. So you have sine of x over 1 times cosine over sine. The sines will now divide out, and that's just going to leave me with a cosine of x. Let me see if I can rewrite that one more time, because it looked like this. So we can see here, these again divide out, and then I'm left with a sine of x over 1, right? Because you can always write it over 1 times a cosine of x over a sine of x. And that's how you can see that those will divide out. That's how we just leave this with a cosine of x. All right, more fractions. You can see, guys, we need to get better at these fractions, right? It's kind of important here. All right, so in this one, again, I'm just going to rewrite everything in terms of sines and cosines. So I have a 1 over a sine of x divided by a 1 over a cosine of x. And so here, if I just multiply by the reciprocal, which is a cosine of x, you can think about it as a cosine of x over 1. So cosine of x over 1, you can see that now I'm just going to be left with a cosine of x over a sine of x. And cosine of x over sine of x, we know is going to equal to a cotangent of x. All right, now just remember, ladies and gentlemen, this is multiplying, right? Now we can go ahead and think about this in the terms of ideas is we want things to divide out, all right? And so we're not adding, so don't worry about this. Remember, we're multiplying here. So I know that if I want to rewrite things in terms of sines and cosines, a couple things we could look at this. I could rewrite this as a sine of x, and then I can multiply this times a negative. Now, 1 over cotangent, you could do 1 over sine over cosine and then multiply by reciprocal, but that's like a lot, isn't it? So what about I think about 1 over tangent as negative cotangent of x? Then I say, well, yeah, I kind of remember this because negative cotangent, I can now rewrite that as a cosine over sine. And that's going to give me exactly what I want. A sine of x divided by 1 times here a negative, we can put the negative up top, doesn't really matter. You got to pick it one way, top, bottom, or outside and front. So cosine of x over a sine of x, but lo and behold, ladies and gentlemen, that's going to give me exactly what I want, is the same expression in the numerator as well as in the denominator. So therefore, this is just going to simplify here to a negative cosine of x. And the last example, I already have the 1 over sine, so I like that here, so I'll leave that. And then, but what I will do is I'll rewrite the tangent as a sine over cosine, sine of x over a cosine of x. You can see those are again going to divide out, which is going to leave me with a 1 over a cosine of x. And now we know 1 over cosine of x using the reciprocal identities is equal to a secant of x. All right, so now let's get into simplifying the expressions to one single expression or number using even or odd identities. So again, one thing I tell students when I'm teaching is whenever you see even odd identities like ding, 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 always be thinking about applying the identity, right? Now, not always is it going to be applicable, but I would say more often than not, ladies and gentlemen, when you have an even odd identity showing up here, like a negative x or a negative angle, you're going to be using the even odd identities, right? So just prepare and get ready for it. So, and I remember, the other thing that's important to remember is that the even odd identities have only sine and cosine only cosine and secant are the ones that are going to remain positive. Like the negative of secant of negative x is the same as secant of x. Cosine of negative x is the same as cosine of x. All the other ones turn to the negate, or turn to the negative version of that. And again, that's what we looked at from the graphs. So first one. Here I have the secant of x. I know that is just equal to positive secant of x divided by cosine of negative x, which I know is just going to be the cosine of x. So now I just need to kind of do some simplifying in this case. And I could say, all right, well, if I multiply by the reciprocal, which would be a secant of x, right? That's a reciprocal, or you can multiply by 1 over cosine if you want to. But think about this, just multiply by the reciprocal and then multiply by secant of x. That's not what the secant of x looks like. What am I writing it up there? I want to write this down below. There you go. So you could think about this as you write it there, and then let's multiply it in red. So if you multiply by the reciprocal, secant of x, we know that's going to make my denominator equal to 1. And then secant, you have to, whatever you do in the denominator, make sure you do in the numerator. So produce your equivalent fraction. So secant of x times secant of x is going to equal a secant squared of x. All right, next one, let's just go ahead and again, one by one, simplify them. Now, it's really important when you have these negatives, use parentheses. I can't even tell you how many times people would change a problem. These are all, this is multiplication up here, right? But what happens when students use negatives and they don't use parentheses, they turn it into a subtraction problem. It's a very, very easy way to get these problems wrong. So this is sine of negative x is a negative sine of x. Cotangent of negative x is going to be a negative cotangent of x. And then divided by, now thankfully cosine of x, we don't need to worry about that, right? That's just going to be a cosine of x. Now we need to simplify our numerator as well as our denominator. So to do that, I can just rewrite my cotangent as a cosine over a sine. Again, the negative you can just leave in the front, right? So I'm actually going to do that. I'll just do it right here to save myself some space. Let's rewrite that up there. So I can stop. I want to rewrite. Okay. So now what I can do is I can rewrite this as a cosine of x over sine of x. Again, that's going using your Pythagorean, your quotient identities. Now, hopefully you see, again, I'll try to slide one in here, the 1, but remember that sine of x, you can think about that as over 1, right? So I have a sine and sine, those are going to divide to 1. A negative times a negative is going to equal a positive. So what I'm going to be left with is a cosine of x all over a cosine of x. So, ladies and gentlemen, a cosine of x over a cosine of x is going to equal to a 1. Over here, again, looks like we have is simply just going to be a, for c, so cosecant of negative x times cosecant of negative x. Well, again, so we know this is a negative cosecant of x, put in the parentheses, times a negative cosecant of x. Negative times negative is a positive, so therefore this is a cosecant squared of x, right? So we know it's now going to be a positive. All right, last one that we have for even odd identities. So I have a 1 over cosine of a negative x. So we know that can be rewritten as a tangent. Here I have a negative tangent of x. Well, again, if you rewrite this, if you expand this out, this is a negative times a negative tangent of a positive x divided by a 1 over a cosine of x, right? So if we rewrite them with the positive angle, you can see that now we have, it's a negative, right? Don't forget to don't lose that, okay? That's why I'm using these parentheses. Well, again, thankfully we know a negative times a negative is just going to be a positive. So therefore we have a tangent over tangent of x. So so I can rewrite tangent as a sine over cosine over cosine, right? That's tangent. And then this is going to be a 1 over a cosine of x. So if I want to multiply by my reciprocal, I'll just multiply by cosine of x on the top and on the bottom. And when you go ahead and do that, you can see again, the cosines are all going to divide out, and it's just going to leave me with a sine of x. All right, simplify the expressions to one trigonometric expression or number using the cofunction identity. So again, remember, whatever graphs look the same, those are the ones that are going to be similar. Sine is same graph with cosine. The transformations go between them. Cosecant and secant, the transformations go between them. Tangent and cotangent, the transformations are going to go between them. So whenever I see sine of pi half minus x, again, ding, 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 I'm thinking cofunction identities. So this is going to equal to the cosine of x. And then I can just rewrite sine, cosecant. I know I need to simplify things. I want to rewrite this in terms of sines and cosines. So I'll rewrite that as a 1 over a sine of x. So now when I multiply them, you can see I have a cosine of x over a sine of x. And again, cosine of x over a sine of x is simply just going to be a cotangent of x. All right, cosecant, I know that is going to be reciprocal with a secant of x. And that's going to be times a sine of x. And cosine, we know, is going to be the same thing as sine and secant. Well, this is kind of cool. You can see that in this case, since our functions are being separated by multiplication, I know the sines are going to divide out. I know the secants are going to divide out. So therefore, this is simply just going to equal to a 1. Next one. So we have tangent. We know that's going to equal with cotangent. And sine, we know that's going to be the same thing as cosine of x. Secant is going to be the same thing as cosecant of x. Okay, so now to simplify this, again, I'm going to want to rewrite, I want to get these terms in sines and cosines. So cotangent, we know that's going to be a cosine of x over sine of x. I have a cosine of x. I'll just rewrite that as a cosine of x. And then cosecant, I'll rewrite that as a 1 over sine of x. So again, when you look at this, I know I can multiply these straight across. And what you see here is I'm going to have a cosine of x over a sine of x. And that's all be divided by a cosine of x all over a sine of x. Well, again, guys, it doesn't matter what the expressions are. If they're exactly the same in the numerator and in the denominator, we know they're going to be equal to 1. So this simplifies down to 1. Cotangent, we know that's equal to cofunction identity is going to be a tangent. Sine, we know the cofunction identity for that is going to be cosine. So we could rewrite tangent as sine over cosine. So sine of x over cosine of x, and then I can rewrite this as cosine of x. And if you're going to multiply by the reciprocal, I would just, instead of doing secant, I would rewrite this as 1 over cosine. So that's cotangent, that's going to be tangent, that's going to be 1 over a cotangent of x. And sine, that goes to cosine. Oh, I think I actually wrote this problem wrong. Sorry, guys. That's actually supposed to be a cosine. That's why. I was wondering, I'm like, that doesn't simplify. There you go. So that's supposed to be a cosine of pi halves minus x. So when you apply your identities in this case, what you would get is going to be a sine of x. Sorry, I'll try to make sure, hopefully that's fixed in the document you have. So for tangent, we have that's the sine of x over cosine of x. And then for cosine, or for sine, we'll just rewrite that as a sine of x. And then if you want to multiply by your reciprocal, rather than using cosecant, let's use the 1 over sine of x. I think it's just easier for us to see. Those are going to divide out. And then here we have a 1 over sine of x. See, those are going to divide out. So now you're left with a 1 over cosine, which we know, ladies and gentlemen, is going to be a secant of x. All right, simplify the expressions using powers of trig functions. So just remember, ladies and gentlemen, that if I have a sine of x times a sine of x, we rewrite that as a sine squared of x, okay? We don't write it as sine x squared. So we don't want to write it like this because this implies that our angle is being squared, not the quantity, not the function sine of x, okay? So don't write it like this, and just remember that's what these represent. So a lot of times, just to understand this, just break it up. So if I have a sine of x divided by sine squared of x, remember that's a sine of x times a sine of x. Well, doing the division property, we know this simplifies to a 1 over sine of x, which is simply going to be a cosecant of x. So let's say 1 over a sine of x simplifies too. All right, over here, tangent squared of x. Remember, that's a tangent of x times a tangent of x, and that's going to be divided by a tangent of x times a secant of x, which again, I can think about that as a 1 over a cosine of x, right? So let's simplify that. So over here, I'm going to have my tangents are going to divide out. Actually, you know what? Let's just rewrite that because I'm going to do it one more time. So that'd be times a cotangent of x, cosine of x. All right, so now I'm left with a tangent of x over cosine of x. Again, I'm going to write tangent as a sine of x over cosine of x divided by a cosine of x. And again, did I write that? Tangent squared, I got those right. But again, tangent of x, sine squared over cosine squared. No, I wrote this wrong. Tangent squared, yeah, tangent over secant. That's a cosine, sine over cosine. Oh, that's secant. I'm an idiot. I was wondering. I'm like, what the heck am I doing? Why did I write that as secant? I was thinking I was doing I was doing the math already in my head. So that's what you get, guys, for some just natural teaching, not going off a script or pre-recording or doing any edit. This is just me, just like I'm teaching inside the classroom. So secant I can rewrite as a 1 over cosine of x. Now to multiply by my reciprocal, I'll multiply by the cosine of x over the cosine of x. Again, remember that's in the numerator, that's in the numerator, those divide out, those divide out. Whew, we are now just left with a sine of x. Okay, perfect. This one, fairly easy, but we'll take it. Cosine of x times cosine of x, remember, ladies and gentlemen, is a cosine of x, quantity squared, which we like to write as a cosine squared of x, okay? So that's what we're going to get there. Just be comfortable with how we write that. So here I have sine of x over tangent of x. Make sure it's not squared, or I know I kind of wrote that in there. So let's rewrite tangent as sine over cosine. So I have a cosine of x times a sine of x over cosine of x. Remember, that's over 1. So those are going to divide out, and that's over a sine squared of x. So now I can rewrite this as a sine of x divided by, now remember, sine squared of x is a sine of x times a sine of x. So now we can apply the division property. I'm left with a 1 over a sine of x, which now I can go ahead and use my reciprocal identity to say this is going to be equal to a cosecant of x. All right, got more. So simplify the expression to one sigma trigonometric identity using the Pythagorean identities. So Pythagorean identities, remember, when I was first teaching this, I showed you they don't always have to look exactly the same. What I want you to kind of be triggered on is when you see a trigonometric function squared, think ding, 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 Pythagorean identity, all right? Sometimes we're gonna have to do some manipulation, but I'll explain that as we get to them for these problems. So sine squared plus cosine squared, hopefully you're like, oh, I already know that one, Ms. McLogan. That's equal to 1 over a tangent squared. Now remember, 1 over tangent is cotangent, so 1 over tangent squared is just going to be a cotangent squared of theta. All right, 1 minus cosine squared of theta. Now this is where a lot of students are like, I don't know how to do this. Like, where does this work? So remember that if we have a sine of squared of x plus a cosine squared of x is equal to 1. Now what happens, remember when I was like dividing both sides by sines and cosines? Yeah, you can do that to get the other trigonometric identities. You can also just like subtract, right? What happens if I subtract a cosine of x on both sides? Cosine squared of x. So now what I get is the sine squared of x is equal to a 1 minus a cosine squared of x. Oh, so a 1 minus cosine squared of x is equal to a sine of x. So you can see, ladies and gentlemen, this is a sine squared of x all over a cosine squared of x. Now remember, sine over cosine is tangent, so sine squared over cosine squared is just going to be a tangent squared of x. All right, so now we got cosecant squared of x minus a sine squared plus 1. Squared plus 1. That doesn't seem right. Maybe that's supposed to be a minus 1, so a negative. That's supposed to be a minus 1. Dang it. All right, so I got some changes I got to make. That should be a minus 1. Because again, if you think about this, if you subtract 1 and then subtract cosine, if you subtract 1 and subtract cosine, that's how you would get that. So let me show you. Let's rewrite it then. So if I have a sine squared of x plus a cosine squared of x is equal to 1, right? Now, let's say I keep the sine here, but I want to get I got the cosine over to the other side. Actually, let's just do it here. Why am I messing around? If you subtract a 1 on both sides, I get a sine squared of x minus 1 is equal to a negative cosine squared of x, okay? So, got that one done. All right, now what about the cosine squared of x minus 1? I think it just goes important to remember, like, what are these identities again? And remember, for a cosecant, the way that we wrote it out is 1 plus a cotangent squared of x is equal to a cosecant squared of x. All right, so again, if I was to do cosecant of x minus 1, if you basically just subtract a 1 on both sides, you get a cotangent squared of x is equal to a cosecant squared of x minus 1. So with a little manipulation, you can see how we got this equation and then we got that equation. All right, so now let's rewrite what we got. So on this left-hand side, this actually simplifies to a cotangent squared of x, and our denominator is now going to divide to a negative cosine squared of x. Okay, so cotangent, remember, is cosine over, maybe did I want that one over there? I don't know, maybe I'll have to rewrite this. So let's rewrite this out. I'm not sure if I might have written this problem wrong. So cotangent is a cosine squared of x. No, we'll be okay. Cosine squared of x over a sine squared of x. And then over here, this is a negative cosine squared of x, right? So now to multiply by the reciprocal, we're going to want to multiply by a 1 over cosine squared of x, and do that over here. So a 1 over a cosine squared of x. Just remember we have this negative, right? The negatives are not dividing out. So you can always take the negative from the denominator, put it in the numerator, or put it out front. In this case, we're going to put it out front. And then these are going to divide out. So I'm left with a 1 over sine squared of x. 1 over sine is cosecant, so a 1 over sine squared is going to be a cosecant squared. And just remember there's that negative, right? So my final answer, since I ran out of room, is going to be a negative cosecant squared of x. All right, and D. So in D, in this case, again, looking at this, we have so if I have the 1 plus cotangent squared of x is equal to a cosecant of x, what I can do is if I can subtract the cosecants on both sides and then subtract the cotangents on both sides, and that's going to leave me with a cotangent squared of x, or sorry, negative cotangent squared of x. And then I need to remember, well, what is 1 plus tangent squared of x? Hopefully you remember, if you go back up to those identities, you can realize that it's just simply equal to the secant squared of x. So now let's go ahead and simplify these. So cotangent can be rewritten as, again, a cosine squared of x all over a sine squared of x. And then this can be rewritten as a 1 over a cosine squared of x. And that is not going to work because I'm going to multiply by, oh, that was a secant squared of x. That's not going to work. That's going to give me a cosine to the 4th power. I don't really want that. So let's maybe rewrite this on the fly. Let's do a different one that I would want. I don't mind the negative, but rather than getting a, what if I did this as a, let's see, if I wrote this as a 1 plus tangent squared of theta is equal to a secant squared of theta. So if I did a 1 minus a secant squared of theta. Let's see what that would be. I'm just going to change this problem up on the fly. I'll have to change this document, so I apologize for that. So what about if I rewrite this as a 1 minus secant of theta, secant squared of theta, cancel that one out, and then rewrite this. I like the 1 plus tangent squared of theta. So 1 plus tangent squared of theta. Okay, so here, again, you'd have to subtract the secant and then subtract the tangent. So therefore, that's going to leave me with a negative tangent squared of theta. And then over here, we know that 1 plus tangent of theta is equal to a secant squared of theta. All right, so now we have if you were to kind of rewrite these, actually, you can multiply if you want to, secant of theta. Okay, so it's sine over cosine, then 1 over cosine. So I think that's what I'm going to get. That's what I want. So if I rewrite this as a sine squared of theta all over a cosine squared of theta, and that's a negative, divided by a 1 over a cosine squared of theta. Yeah, that's going to work. So now all I simply need to do to get rid of my cosines in my denominator is I'll just multiply by a cosine of theta over a cosine squared of theta. Make sure it's squared too, right? So now those divide out, and now my final answer is going to be a negative sine squared of theta. All right, so we're going to change the answer. I don't know where I wrote that one up there and what I did, but that's going to be the answer we're going to work with, or the problem we're going to work with. All right, so we don't have too many more, but again, those are like the basic simplifying trigonometric identities. But a lot of times when we are simplifying identities, there's operations that are involved. We have multiplication, or also we have addition and subtraction, or we have factoring. So there's a lot of things we need to do, not just to simplify an expression, but a lot of times we need to be able to apply operations. So that's what we're going to get into these next couple examples. So if I have cosine of x plus sine of x, remember, ladies and gentlemen, that is cosine of x plus sine of x times cosine of x plus sine of x. So it's very important. Do not just distribute that square to both of those terms. This can be rewritten as a cosine of x plus a sine of x times a cosine of x plus a sine of x, right? So you can apply distributive property, you can apply a FOIL, whatever you want to think about, or how you remember how to do this. So cosine of x times cosine of x is going to be a cosine of x squared. Cosine times sine, cosine, and then you have sine times cosine. Those are exactly the same. Well, I'll just rewrite it out. Sine times sine of x times cosine of x. And then we have cosine of x times sine of x. And then we have sine of x times sine of x, which is going to be a sine squared of x. Okay. Now, remember, since these are exactly the same, 2 times 3 is the same as 3 times 2, right? They both equal 6. So we can combine them to give us a 2, and it doesn't matter which order you want to write. And then also remember, cosine squared of x plus sine squared of x is equal to a 1. So 1 plus a 2 sine of x cosine of x. So again, remember this is just applying the operations and then simplifying if we can. Not all of them are going to be able to be simplified. But we're going to try our best. So in this one, again, we have multiplication, but here's something kind of interesting. Notice how my first 2 terms are exactly the same. Notice how my last 2 terms are exactly the same. Notice how one's positive and one's negative. Hopefully, if you remember from your good old Algebra 2 days, this is going to be the difference of 2 squares. We can rewrite that, right, as an a squared minus a b squared. So this is going to be a cotangent squared of x minus a cosecant squared of x. Now, another thing that I want you to kind of recognize that the cotangent and cosecant are related via the Pythagorean identities. So I can actually further simplify this. Yes, I can apply the operation, but again, it said to simplify or look to simplify. So I can rewrite a cosecant, remember, as a cotangent of x plus 1, or a 1 plus cotangent of x. So I can rewrite this as a cotangent squared of x plus 1. Now again, apply distributive property, and you get a cotangent squared of x minus a cotangent squared of x minus 1. Well, those are going to divide out, and we're just going to be left with a negative 1. Over here, again, we can just apply distributive property here. It might be easy or might be helpful in this case before you actually get into multiplying that you just remember that secant is 1 over a cosine of x, and cotangent is cosine of x over a sine of x. Okay, so again, a lot of times, the more practice you get on this, you just kind of do this in your head. But be careful, once you start doing things in your head, that's also where a lot of mistakes are going to happen. But sine of x times 1 over cosine of x is going to be a sine of x over cosine of x, and sine of x times cosine over sine, those are going to divide out, or your sines are going to divide out, so you're just going to be left with a cosine of x. So we know sine of x over cosine of x is going to be a tangent of x plus a cosine of x. All right, now over here, you could go ahead and distribute this. But again, remember what I said, ding, 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 think of your Pythagorean identities. Tangent squared of x plus 1, ladies and gentlemen, is just going to be a secant squared of x. 1 minus a sine squared of x, if you manipulate it, is simply just going to be times the cosine of x, cosine squared of x. And just remember, secant is 1 over a cosine squared of x. So times a cosine squared of x, we know that those are reciprocals of each other, so therefore it's just going to equal 1. All right, now let's get into adding and subtracting. Now, I know, ladies and gentlemen, most students hate adding and subtracting. So this might be the perfect part of the lesson where you're like, let me zero in and make sure I know how to do this. Because remember, if I have a 1/2 plus a 1/3, since they do not have the same denominator, to get the same denominator, I need to multiply by a 3 over 3 over here and a 2 over 2 over here. So therefore, I'll have a 3 over 6 plus a 2 over 6, which equals a 5 over 6, okay? So don't forget that, ladies and gentlemen. Don't forget it. It's very important to remember. Wanted to make sure you remember how to do your fractions. Okay, so that's exactly what we need to pay attention to. When we're adding and subtracting over here, we got to have the same denominator. So that's immediately going to be our first thing. Now, in this case, the LCD is not always going to be the product of your two denominators, but that's an easy way to always look into first, all right? So, in this case, to get my common denominator, I will just use the product because they don't have anything else in common. So the sine of x times cosine of x will be my LCD. So a lot of times I'll write that out in front. I'll say the LCD is a sine of x times a cosine of x. So here I'll multiply by a sine of x over a sine of x. And then over here, I'll multiply by cosine of x over a cosine of x. Now let's do some simple math here real quick. Cosine of x times sine of x, that's going to equal 1. Sine of x times sine of x, that's going to be a sine squared of x. And that's going to be all over cosine times sine. Cosine of x times a sine of x. Now again, before we get anywhere far, ladies and gentlemen, we need to remember that to simplify, and we can see that 1 minus sine squared of x, that can be reduced to a cosine squared of x. So it's a cosine squared of x all over a cosine of x times a sine of x. And again, remember that's a double like sine of x, right? So you can think about that that's 2 cosines of x being multiplied. So that's going to divide out with that, and that's going to leave me with just 1 cosine over sine, which is just going to give me a cotangent of x. Cotangent of x. Voila. All right, this one. 1 over sine squared plus a secant squared over tangent squared. Well, common denominator is simply, in my case, is just going to be a product of the two. So let's go ahead and get right into this multiplying both sides. So I have a tangent of x over a tangent of x, and then over here I'll multiply by a sine squared of x times a sine squared of x. All right, so now in my denominator, so over here I'll have a tangent of x. Why don't I multiply by sine of x? Is that what I want from on that one? Tangent of x. Yeah, okay. So I'll have a tangent of x plus, now here I can rewrite a secant of secant squared as 1 over cosine, right? So 1 over cosine times sine squared would be a sine squared over cosine squared, which would be a tangent squared of x, divided by a tangent of x times a secant squared of x. Okay. Now, we didn't get into this yet, but we're going to get into it. So you also recognize that here I have a common term of a tangent. So I can factor out this tangent of x. When doing this, I get a 1 plus a tangent of x. And then over here, I have a tangent of x times a secant squared of x. So now those tangents will divide out. And that's just going to leave me with a 1 plus tangent of x all over a secant squared of x. But I actually didn't get into factoring that, so I'm about to. So if you didn't do that, I won't be mad at you if you try that, but I just want to kind of give you a more simplified version. All right. Whew. Well, just like we found the product, like 2 and 3, we just multiply them. In this case, we do the exact same thing, right? So again, like don't shy away from this, ladies and gentlemen. Multiply by the reciprocal. So this would be a 1 plus cosine of x. Here would be a 1 minus a cosine of x. And whatever you do in the denominator, you have to make sure you do in the numerator. So over here, so it's 1 plus a cosine of x. Okay, so again, this is going to give us a difference of 2 squares in the denominator. So in the numerator, I get a 1 minus a cosine of x plus a 1 plus a cosine of x. And then I will get a 1 squared minus a cosine squared of x, right? That's the difference of 2 squares. But hopefully you recognize this 1 minus a cosine squared is going to give us the Pythagorean identity, which is going to be a sine squared. And then in my numerator, you can see that those are going to divide out. So this is going to give me a 2 over a sine squared of x, right? Because that's going to be Pythagorean identity. And then that is going to be 1 over sine is going to be the cosecant. So my final answer is a 2 cosecant squared of x. Cosecant squared of x. All right. Last one with adding and subtracting. You might be sick of it. I may be too as well. So again, multiply. There's nothing else they have in common here. So I'm going to multiply by 1 plus a sine squared of x on the right-hand side. And on the left-hand side, I'll multiply by the cosine of x. Okay, so over here, I'm going to get a cosine of x, cosine squared of x, apologies. And then over here, I'm going to get a 1 plus sine of squared, which is, okay, I guess I need to multiply that out. So again, applying distributive property, I'll do this a little bit quicker. So this is going to be a 1 plus a, since it's the same thing, it's a binomial squared. So I know it's going to be 1 times a sine squared of x, and that's going to be plus a sine squared of x. And this is, again, all over a cosine of x times a 1 plus sine of x. Okay, so we know that this is equal to a 1, right? So 1 plus 1 is going to be a 2. So I have a 2 plus a 2 sine squared of x divided by a cosine of x times a 1 plus a sine of x. Okay, and then now, ladies and gentlemen, I know that I can factor out a 2. So by factoring out a 2, I'm left with a 1 plus a sine squared of x in the numerator. And then over here, again, the denominator is exactly the same. But you can see the numerator and denominator are now exactly the same. So these expressions, since they are exactly the same, and since my terms here and here are separated by multiplication, I can divide these out. So I'm just going to be left with a 2 over cosine, which is simply going to be a 2 secant of x. All right. The next one, the fun part. So remember rationalizing the denominator? Back in your algebra 2 days, if we had like 1 over the square root of 3, and we wanted to get rid of the radical, we say we don't want to divide by the square root of 3. Well, what would we do? We would rationalize the denominator. How did we do that? We'd multiply by the square root of 3 on the top and on the bottom, and therefore we get the square root of 3 divided by 3. No longer do we have a radical in the denominator. And then we also came up with, well, what about if I had 1 plus the square root of 3? What did we do there? In that case, what we needed to do was multiply by the conjugate, 1 minus a square root of 3. The reason why we want to multiply by the conjugate is because that produced a difference of 2 squares. So in these examples, when you have a binomial in this case, that's exactly what we're looking into doing. We're looking to what we're doing is we're looking to create a perfect square trinomial. Now, why would we want to create a perfect square trinomial with trigonometric functions? The reason why we want to do it with trigonometric functions is because then that's going to create the Pythagorean identities that we can further simplify. So let's go and take a look at the first example. If you know that the conjugate of this would be a 1 minus a cosine of x, and you multiply by a 1 minus cosine of x on the top and the bottom. So the numerator is going to be exactly as it is. So that's going to be a sine of x times 1 minus a cosine, not cosine squared of x, just a cosine of x. And then in my denominator, what we have here is, again, this is a difference of 2 squares. So this is going to be a 1 minus a cosine squared of x, right? So that's going to be a 1 minus cosine squared of x. And again, think about your Pythagorean identity. Sine squared plus cosine squared equals 1. If you subtract a cosine squared on both sides, this is just equal to a sine squared. So I can actually just cancel that out and say that's equal to a sine squared of x using my Pythagorean identities, which now those will divide out. So my final answer is a 1 minus a cosine of x. All right, the next one, same exact thing. Think about multiplying by your reciprocal. What's the reciprocal in this case? Now, it's important in this case that we just think of like, all right, well, the opposite, the conjugate. Sorry, now my brain is starting to go. This would be a long lesson inside the classroom, but you guys are getting the benefit of the full lesson. So I'm going to multiply by secant of x times a secant minus x. So this is going to produce a tangent squared of x times a secant of x minus 1. Denominator, though, now is going to be a secant squared of x minus 1, or minus a 1 squared. So remember, it was tangent squared plus 1 equals a secant squared, right? So again, you can see how this is going to simplify over to a tangent squared of x, which now those will divide out, and we're just left with a secant of x minus 1. All right, let's go and do it again. So 1 over secant of x minus a tangent of x. So multiply by the conjugate would be simply multiplying by, I want to do, I wonder what I was trying to do with this one. Doing a lot of sines and cosines. Yeah, okay. What's this? So in this one, I have if I multiply by the conjugate, this would be a secant of x plus a tangent of x divided by a secant of x plus a tangent of x. All right, so we have a secant of x plus a tangent of x divided by a secant squared of x minus a tangent squared of x. Okay, so I think the important thing that I always like to do when I'm looking into these, or when you're trying to simplify this, I can't really simplify anything further here if they're not in the same trigonometric terms, right? So what I'm going to want to do in this case is I'm going to want to rewrite secant and tangent in the same term. So I know 1 plus tangent squared is equal to secant squared. So if you subtract the 1, then you'd have a tangent squared is equal to secant squared minus 1. So I can rewrite this as a, let me just cancel it out because I don't want to rewrite all that. I can rewrite that as a tangent squared plus 1, tangent of x plus 1. Right? So now if you think about this, tangent squared of x plus 1 minus a tangent squared of x, now we can say that though these are going to divide out, and now I'm just going, or not divide out, they're going to subtract to 0. So now I'm just going to be left with a secant of x plus a tangent of x. But don't forget here, that's minus 1, so that's going to be divided by 1. So therefore, since it's just divided by 1, you're just left with a secant of x plus a tangent of x. All right, I don't want to do this one. This one looks exactly the same. So I'm going to do, since we're already this far in the video, let's just make up one and see how it works. I don't know if this one's going to be a good problem or not. So I'm just going to make it up and see what happens. So let's see, we have, rather than tangent, let's do a cotangent of x plus a cosecant of x. So if this works out all right, then I will keep this, okay? So I'll probably update it on there, but let's see how this one would be. So if you're gonna multiply this, this one out, so we'd multiply by the conjugate, and again, I'm making up this problem, so hopefully it is going to work. Cosecant of x, so I multiply by a cotangent of x minus a cosecant of x. Okay, so in the numerator here, we're just going to leave this negative 2 times the cotangent of x minus a cosecant of x. You could distribute that through, but I always prefer to like keep things the way they kind of are in that case. I don't like to kind of ruffle the feathers per se. Like leave it there. If we realize we need to divide it out, then we can. All right, so I think 1 plus cotangent squared is equal to cosecant squared. So if I have sine squared plus cosine squared, if I divide by sine, that'd be 1 plus cotangent squared is equal to what, sine over sine divided by sine, cosine over sine, 1 over sine is cosecant. So yeah, so that I just got to remember. So 1 plus a cotangent squared of x is equal to a cosecant squared of x. Okay, so then in this case, I'm going to get a cotangent squared of x minus a cosecant squared of x. And again, kind of like what we are doing over here, ladies and gentlemen, let's rewrite the cosecant in terms of cotangent. So again, to do that, what I simply can do is I can just, I can subtract the 1 on both sides, and that would be, no, I already have this. Why don't we just rewrite this cosecant in terms of cotangent, which is right there. So I can rewrite this as a 1 plus a cotangent squared of x. There you go. Okay, so now I'm going to have now my cotangents are going to subtract out. Right, so let's cancel that one out there. So now my cotangents are going to subtract out, and I'm going to be left with a negative 1. So my final answer here is I have a negative 2 times a cotangent of x minus a cosecant of x. But then remember, there's a negative here, right? So that's all divided by negative 1. So now those are going to turn to a positive, and you can write your final answer as a 2 cotangent of x minus a 2 cosecant of x. So now we can go ahead and distribute that through. So I'll have to double check that. Hopefully I worked that one out. All right, we are on to the last one, ladies and gentlemen. I know this is a big one, but I'm telling you, ladies and gentlemen, if you've gone through these examples with me, you're at this part of this video, you have to be feeling good about yourself. You have to be able to like, hopefully things are kind of come together, because before we get into verifying, before we get into solving, all of the stuff that comes up later in other lessons is all based on you understanding how to manipulate and simplify your trigonometric identities. So again, you can always go and get a download of this down in the links below. Or if you like this instruction, but you also want the full course on precalculus, then I have links on my precalculus exam or precalculus course down below as well. All right. So factor the expressions, then simplify. So this is kind of where I got into. Remember, I was like, oh, I haven't taught that yet. So oops. But remember, just like any kind of trigonometric expression, guys, we can always factor terms out. If I have x, squared plus x, I can factor out an x and rewrite that as an x plus, or blah, blah. I can factor that out from a x plus 1. So if you ever get confused with this, a lot of times what I always tell my students to do is just treat things in terms of like x's and y's. It doesn't matter what is x, doesn't matter what's y. You could think about this as a x squared times a y squared minus an x squared. What can you do? What could you factor out? You could factor out the x squared, right? And that's going to leave you with a y squared minus 1, right? So don't let the trigonometric identities mess you up. Hopefully you recognize in this case, though, that the sine squareds are the same. So I could factor out a sine squared of theta. And that's going to leave me with a cosecant squared of x minus 1. And again, though, ladies and gentlemen, always to remember that when you're thinking about these, is we always want to be looking into what are our Pythagorean identities. So cosecant squared of x, remember that can be written as a cotangent of x. So I have a sine squared of x that can be written as a cotangent squared of x. Cotangent is going to be a cosine over sine. So the sines are going to divide out. So therefore, I'm left with a cosine squared of x. Over here, again, you see the fourth and you're like, crap, I don't know how to factor anything to the fourth power. So again, let's just look at the algebraic manipulation. X to the fourth minus a 2x squared plus 1. Hopefully you recognize, ladies and gentlemen, if you were to factor this in binomials or for quadratics, hopefully you recognize, well, I can factor this as a product of two binomials, right? What two numbers multiply to give me 1, they're going to add. So I know this has to be -1, right? They're multiplying to give me a positive 1, but they're add to give me -2. It has to be two negative ones. And then over here, this has to be an x, but x times x gives me x squared. I need it to the fourth power. So I need to use an x squared and an x squared. So I'm going to use that exact same thinking to be like, all right, well, let's just replace our x with a cosine of x. So therefore, this would be a cosine squared of x minus 1 times a cosine squared of x minus 1. What am I doing? Minus 1, which is the same thing as, now again, this is the same thing as a cosine squared of x minus 1 quantity squared. But remember, what is a cosine squared of x minus 1? If you remember from your Pythagorean identities, that is a sine squared of x. So we have a sine squared of x squared, which is going to be a sine to the fourth power of x. All right, another one, again, just think about the algebraic manipulation here, is if I had a 2x, no, I want red. So if I had a 2x squared plus a 3x plus 1, again, factoring, right? So we know I can break this up into a binomial times a binomial. So x times x. I know to get my 1, it has to be a positive 1. Since my middle term is positive as well, I know that these two terms have to be plus 1 and plus 1. That wasn't even hard factoring, right? It wasn't even that bad. So now, again, just replace my x with my sine of x. So I can rewrite this as a 2 sine of x plus 1. And then here, I can rewrite this as a sine of x plus 1. Unfortunately, ladies and gentlemen, though, there's nothing squared, so don't try to be doing anything with your Pythagorean identities. Over here, think about, again, difference of two squares, right? A to the fourth minus b to the fourth can be factored down into an a squared minus a b squared times a squared plus a b squared. This can be factored down into an a minus b times an a plus b, right? So don't forget that. So that would be times a squared plus a b squared. So you could do it kind of with me on from there, or you could do it the algebraic way and then just kind of distribute things as you see fit. I kind of leave that there for you. There you go. Okay. But I kind of want to factor this down, kind of go from there, because we can also simplify things a little bit further. Because actually, if you do this, you might actually come into a problem. Because if I break this up, because here's what I'm thinking. I'm seeing this a squared plus b squared. If I get a sine squared plus cosine squared, what do I know that's equal to? I know it's equal to 1, right? So let's break this up into a sine squared of x minus, no, sorry. Yeah, I was right. So sine squared of x minus a cosine squared of x times, I am running out of space though, times a sine squared of x plus a cosine squared of x. Okay, but what do we know about this, ladies and gentlemen? We know that's equal to 1, right? 1. That's awesome. So now I have a sine squared of x. Now, if I want to simplify these, I do see the Pythagorean identity squared. So I think Pythagorean identities, right? So I know sine squared plus cosine squared is equal to 1. You can read it in terms of sines. You can rewrite it in terms of cosines. So let's actually rewrite the sine. I can rewrite sine in terms of cosines as 1 minus a cosine squared of x, and that's still minus a cosine squared of x. And then remember that's times 1, right? So we don't really need to write the 1, but well, riddle me this. So negative cosine squared of x minus a cosine squared of x. You owe me $1, you borrow another $1. $1, you now owe me $2. So this would be 1 minus a 2 cosine squared of x. And voila. All right, for this one, when we have 4 terms, if you remember polynomials and grouping, whenever we have 4 terms, we want to apply the grouping method, right? So if I have a x cubed minus a x squared minus an x plus 1, remember the grouping technique kind of works like this. You group the first 2 terms, right? And you group the last 2 terms, but you got to change that to a minus a negative. And then you group the last 2 terms. Then you factor each GCF. So I can factor out an x squared here. I'm left with an x minus a 1. And then over here, I can factor out a negative 1, and I'm left with a x minus 1. That's the grouping technique. So let's do this with secants and see what we get. So over here, if I have a secant cubed of x minus a secant squared of x minus a, well, I'm going to change this to plus a negative secant of x plus 1. So group the first 2 terms, group the second 2 terms, right? You always got to separate by addition from on there. So all I did was change it from a subtraction to add a negative. So now I can factor out a secant squared of x. That's going to leave me with a secant of x minus 1. And then over here, I can factor out just a negative 1. Because again, your goal is to get these to be exactly the same, which is going to be a secant of x minus 1. Now, factor out the secant of x minus 1, since that is shared in both of them. So you're left with a secant of x minus 1, and your times a secant squared of x minus 1. Now again, I'm seeing that secant squared of x minus 1. Immediately my brain that's coming into as tangent. So my final answer is a secant of x minus 1 times a tangent squared of x. All right, last one, ladies and gentlemen. Hopefully again recognize that this is a perfect square trinomial. X squared plus a 2x plus 1. That is, can be factored down into an x plus 1 quantity squared. So again, looking at this in terms of tangent, this would be a tangent of x, plus 1 quantity squared. And really, like, you can just replace it, but I mean, if you think about this and what is the factored form of it, and just think about it in terms of x's, then think about it in tangents. All right, ladies and gentlemen, that is it for my lesson on simplifying identities. This would be a true lesson that I'd go through in classroom. I hope it was helpful. I have more lessons coming up for analytic trigonometry, which you'll see in the videos coming up. But again, if you want to download my resources, then click down below, and I look forward to helping you on another lesson.